Okay, so we have one problem left for chapter 5, which is pretty simple. This is a semi-solid, and when you have a semi-solid transient conduction problem, there are 3 different cases. So you need to, you need to determine, what kind of case that you're going to use. If you look at this, it says that here is the information, assuming that the surface is maintained at the temperature of the water. So it's a constant surface temperature boundary condition whose temperature equation is given here. So we are going to use this equation. So let me write this equation here. T at position x and time t minus the surface temperature divided by the initial temperature of the solid minus the surface temperature is going to be error function of x over 2 times square root of alpha t. So that is the governing equation. Then we want to know how long will it take. So we want to determine this time t. Then let's see, what do we have? For the temperature to reach 50 degrees Celsius, so the temperature of the semi-solid is going to be 50 degrees Celsius. Then what is the surface temperature? Water, 25 degrees Celsius. And what is the initial temperature? 300. So this one is 300 degrees Celsius. And what is x? 25 millimeters, 0.025 meter. And alpha can be determined by thermal conductivity K over density times specific heat. Then we already know density, specific heat, and thermal conductivity. So you can determine the thermal diffusivity alpha, which is 1.34 times 10 to minus 5 meters square per second. So if you calculate the left-hand side, this whole thing becomes 0.009 0.09 is error function of x over 2 times square root of alpha t. Then you can use the error function table to determine whatever the input of this error function. I explained how to use this error function table last Tuesday. So if you use a table, then you can determine the input of this error function, which is 0.0807. Since we already know alpha and x, you can determine time t, which is 1,793 seconds. Okay. So that's everything about chapter 5, and the new homework due date is going to be Thursday next week, as we discussed, right? Today we are going to talk about chapter 7, external flow convection. So in heat transfer, we study 2 heat transfers. The first one is conduction, steady state conduction and transient conduction. We studied steady state conduction in chapter 3 and transient heat conduction in chapter 5. And these are how we are going to, study how we are going to determine heat transfer. But there's one problem. For example, if you want to use, let's say, thermal resistance network, how you determine thermal resistance network? Q is delta T over R, and this R can be, XYZ coordinate system. It's going to be the thickness divided by thermal conductivity K times area. That's for conduction. But for convection, it's going to be 1 over HA, right? What about if it is transient conduction? There are two different ways to solve transient conduction problem. The first one is, just for your example, the first one was lumped system analysis. When you have a lumped system analysis, how did we determine the temperature of the transient conduction problem? We use this equation, T minus T infinite over Ti minus T infinite is E2 minus HA over rho VCT. Kind of good review, right? But so if you want to solve this thermal resistance network, this delta X is going to be the thickness of the conduction. K is the thermal conductivity. You can find it from a property table. Area is going to be, the cross-sectional area where heat is transferring through. And this delta T is going to be the temperature difference. Q is the rate of heat transfer. So we know everything except one. What is that? This H. This H was given in each problem in chapter 3. What about this lumped system analysis? This T is the temperature of the system at a certain time T, and T infinite is the surrounding fluid temperature. Ti is the initial temperature of the solid. Rho is density. You can find it from a property table. C is the specific heat, the same thing. V is volume. A is area. So you know everything. This time T is also known. Then one problem is going to be this H. How did we determine this H? We didn't. It was provided in chapter 3 and chapter 5. So now what we are going to do is that we are going to learn how to determine this H. That's what we are going to do in chapter 7, chapter 8, and chapter 9. Sounds like a lot of, the chapters, right? But not necessarily. The point is, when we talk about material properties such as density, specific heat, are they a constant? Not usual. Usually they are variable. They change with temperature. So for example, when temperature goes up, the density of gas goes down, or for specific heat, the temperature goes up and specific heat goes up. So usually, when you want to determine these thermal properties, you just need to determine the average temperature and evaluate those properties at the average temperature from a table. So as long as you have a table, you can determine them. What about this H? Is there a table for H? No. Why there is no table for H? Because this is not material property. This depends on, of course, the material property as well as fluid motion. So depending on the velocity of fluid, depending on, the surface condition, depending on the material, the properties such as density or thermal conductivity, this one will change. So H value of air in this classroom may not be the same as H value of the air in the hallway. It's not going to be the same H value outside. Why is that? Because the air in this classroom has a different material composition than the air in the hallway. No, we have the same air, 80% nitrogen, 20% oxygen. When you go outside, there's air. Here, 80% nitrogen, 20%, the oxygen. However, the H value of air outside is going to be different from H value inside here. What about H value in Midland? H value in Texas? They're all different because it depends on how, this air flows and also the material property. H value of, the air is going to be different from H value of water in that bottle. Why is that? Because water is much denser than air. So there are many, many factors affecting this H. Now the question is, then can we determine this H by a simple equation or by using a table? No, we can't. So we are going to rely on what? Correlations developed from an experiment. So we are going to learn how to find this H for a given condition. This is the velocity, this is the geometry of the solid, this is the material of the, the solid and, the gas. So let's learn how to determine H. That's what we are going to do. Then why there are 3 chapters? The first chapter is chapter 7, and this chapter 7 is for an external forced convection and chapter 8 is going to be internal forced convection, and chapter 9 is going to be free convection. Then the first thing you want to understand is what they are different, how they are different. External forced convection means there's an external force, maybe fan or pressure drop or anything that will move fluid over a surface, and the surface is not whatever the fluid is not confined, then it is called external forced convection. What about the wind outside? Wind has a velocity, so there's a there is an external force. What is that? The pressure difference. If the pressure, the Mount Pleasant is less than the pressure near the northern area, we have the wind from the north, right? And if it is open to if the surface is open to the wind, then it is called external forced convection. What about the air duct on top of behind this cylinder? There is the same air is flowing, however, it is inside the duct, so it's not completely open. Then it is called internal forced convection. What about air in this classroom? Is there any fan is running? No. However, there should be air circulation in this classroom due to gravity. For example, this is the room. What about, the air at the bottom has low temperature, and air at the top near the ceiling has high temperature. When we have the heater, when we have a vent from the heater is placed on the ceiling, then usually the air temperature near the ceiling is going to be higher than the air temperature at the bottom. In that case, what is the density of air? Density of air goes down when temperature goes up. When the density air goes up when temperature down. So the air at the bottom is going to be heavier than the air at the top. Then nothing is going to happen. It's going to be called stable condition. What about we have air in the room and the temperature at the bottom is higher than the temperature at the top? Then the density of air is going to be low at the bottom, and the density of air at the top is going to be high. So the air near the ceiling is going to be heavier than the air at the bottom. So what's going to happen? The air at the ceiling is going to go down. What is it called? Buoyancy effect. So the air goes up and this one goes down. So there's an air circulation, which is called unstable. Then, in this case, do we have any external force? No, but there is an air movement. When there is an air is moving, there should be convection heat transfer between the surface and the surrounding air. That is called free convection, or some textbooks like to say natural convection. So depending on how this convection occurs, there are 3 chapters, and the goal of each chapter is going to be how we can determine convection heat transfer coefficient H. That's what we are going to study. Okay? Then let's study external forced convection. But before we going forward, there's one thing that you need to understand, which is, by the way, this is 12:51. I'm going to do a review for, the second exam for the last 20 minutes. So please remind me at 1:20 or 1:10, then we can check the attendance and review exam number 2. So what about if we talk about, the convection between air outside and this building? So there's an engineering technology building here. So this is engineering technology building, and there's an air flowing nearby. And this convection, so there should be convection, from the surface of the wall of this building to the surrounding wind, right? And what about there is another building, maybe a library, should be taller than. So this is the library, and there's a wind is flowing nearby. Or, I can go outside. Let's say that I'm standing in the parking lot, and there's an air, blowing nearby me. So are they all the same convection? Not necessarily, right? So if you want to study convection heat transfer for the, for this convection and this one, since there are 3 different, the convections, you should have 3 different governing equations to determine H value. What about if you go to, another city? Or what about if you talk about, the convection between your car and the surrounding air, or pickup truck, or bus? You should have a number of equations to determine H. So how inconvenient it is, right? So in that case, how we can, simplify this kind of analysis. In fluid mechanics, you studied what is called dimensional analysis. So we can do a dimensional analysis. Instead of determining H right away, we can use a dimensionless number that is called Dussel number. And to determine this H depends on the velocity. So when you drive your car, when you go faster, the convection between the car and the surrounding air is going to increase, right? Like in summer, if you open the window and when you drive faster, you feel that it's cooler. Why is that? There's more convection. There's more H value, higher H value, right? So when you drive faster, the H value goes up, right? What about in one of the winter day, if there's no wind, if you're standing outside, is it very chilly? Not really, but what about, there's a very strong wind? You may feel that it's freezing. Why is that? Because H value goes up when velocity goes up. So there is a dimension of this number to account for the velocity, fluid motion. That is called Reynolds number that you studied in fluid mechanics, right? You didn't study fluid mechanics? That's a prerequisite. You studied fluid mechanics, right? Now you remember Reynolds number, okay? And what about your the convection between me and the wind outside? And what about if I jump into a swimming pool in the sack? Then the convection heat transfer between my skin and the water is going to be different from the convection between myself and air nearby, right? So there should be another dimensionless number to represent the material property that is called Prandtl number. So let me give you just the basic equation that is this Nielsen number that represents this H is going to be a function of Reynolds number and Prandtl number. And we need to have some coefficient, that is coefficient C times Reynolds number to the power m times Prandtl number to the power n. So this is typical Nielsen number correlations. So to determine H, what you are going to do is there are two major things affect this H. One is fluid motion, how strong this wind is. The other one is material property. Imagine that the standing in the cold weather outside or jumping into the freezing water. That can be explained by Reynolds number for the fluid motion and Prandtl number for the fluid property. So going back to the movie Titanic, the guy didn't know about Prandtl number, so he stayed in the water, and the girl knew the heat transfer, so he knew that, so decided to be on top. Right? No, that's my guess. So this is a typical Nielsen number correlation. So what you are going to study in chapter 7, 8, and 9, there are a number of Nielsen number correlations are already developed by engineers, scientists. So we are going to learn how to select the right Nielsen numbers for the given, the convection, the problems. So depending on the velocity, depending on the geometry, depending on the material properties, then we are going to learn how to select the right Nielsen numbers and then use that Nielsen number to determine H. So that's going to be the first half of chapter 7, 8, and 9. What is the other half of the problem? Then once you determine H, use the governing equations that we studied in chapter 3 and chapter 5 to determine unknown temperature T or the rate of heat transfer. So basically, you already know the half of how we are going to solve the problems. One thing that you didn't know, one thing that you do not know is H. So we are going to study how to determine H, and once we learn this is the H value for this convection problem, then you will use either the thermal resistance network or spin analysis or the lumped method or approximate method That's how you are going to solve them. Okay? Now, even though there are 3 chapters left over, pretty simple. I can teach all 3 chapters today, but we need to do a review. So we are going to study only external forced convection, okay? Then, to study Lucent number correlations for external forced convection, we need to, review some characteristics of external flow, which you are supposed to know already from fluid mechanics, but maybe we can do a quick review, okay? So what happens in external forced convection? When there is fluid flow, uniform flow, let's say there's a air is blowing in this way, air, and whose velocity is 10 meter per second. So when I say 10 meter per second, this is 10 meter per second, this is 10 meter per second, so it's a uniform velocity, okay? And let's assume that arrow, the length of arrow, represents velocity, okay? So the shorter arrow means low velocity, longer arrow means high velocity. Then, to have an external flow, we are going to introduce a surface. So there's a solid surface, like that. So air is blowing this way. What's going to happen? Nothing, just, the uniformly flow in this direction? Not really. There should be what? Friction between the surface and the fluid next to it, right? Because of the friction, what happens? The fluid molecule is going to be stopped at the surface. So the fluid velocity at the surface is going to be 0. In reality, it could be 0 or it can slip on the surface. Like, when you're walking on ice, sometimes you slip, right? That could happen, but in undergraduate fluid mechanics, we assume that, there's no slip. Why? If there's a slip, it's going to be complicated. So let's assume that there's no slip, which is okay in most engineering processes, okay? Because slipping is very quite rare and unique. So assuming that no slip condition, what's going to happen on top for the fluid molecules right on top of this one? So the guy, the fluid molecule on the surface is stopped. I'm next to it. I can freely, go this way. Not really, because I will be slowed by the fluid particle, which is stopped, right? So the velocity of the fluid molecule right on top of this one is going to be slowed. So the velocity of the fluid molecule right on top of it is going to be about this much, maybe 1 meter per second or 2 meters per second. What about the fluid molecule on top of it? Slightly faster. What about on top of it? Or still, it is far away from the surface, so I have a uniform velocity like that. So once this one is slowed, it's going to affect the fluid particle on top of it. It's going to affect the fluid particle on top of it, and keep going on, like an infectious disease, right? So about this much later, this much distance later, that we have more fluid particles are slowed due to the friction from the surface, like that. More fluid particles, and then away from the surface, we have a uniform velocity, which is 10 meters per second, the same as this one, 10 meters per second. And here, more fluid particles are slowed. Than uniform. So when we say uniform velocity, we say velocity u, usually v, u means velocity in x direction. So if we say this is x direction, the first derivative of x is going to be u. So we say u is the velocity and When it is uniform, we say U infinite. This infinite means constant. So the velocity that is not affected by the, the surface. And up to here is affected by, the friction from the surface up to this much, So if you connect the region where velocity has been decreased, this is called what? Boundary layer. This is what you have studied from fluid mechanics, right? If you don't remember, that's okay. I just show you so you can see, what's going to happen in terms of fluid mechanics. Now, we are not studying fluid mechanics. We are studying convection heat transfer. So let's talk about, the let's talk about this one on a heat transfer point of view. So I'm going to use this red, show the velocity. So now this is not a velocity anymore. So each arrow represents temperature. So let's assume that the temperature of the air is maybe 90 degrees Celsius. It's hot air, maybe inside the convection oven or something. Then there is a solid surface. And the surface is going to be at maybe 20 degrees Celsius. Then what's going to happen? There's to be heat transfer from the fluid to the surface in this direction. Why? The temperature of the fluid is at higher temperature than the temperature of the surface. Due to the second law of thermodynamics, heat transfers from the fluid to the surface. Because of that, what happens? So do we expect that, the heat transfer directly from this particle to the surface? No, initially, the heat transfer takes place from the fluid right next to the surface. So right next to the surface, we have a decreased temperature about this much, but away from that, still 90 degrees Celsius. So here maybe you can say 40 degrees Celsius or 30 degrees Celsius, but here 90. And there's a heat transfer from 90 to 40, so it goes on, so the temperature is going to reduce further from the surface. So about this here, maybe 20, 30, 40, 50, and 90. What about here? More heat transfer from the fluid to the surface. So 20, 30, 40, 50, 60, 70, 80, and 90. And when we say the temperature of the fluid, we say T infinite, just to show this is the uniform temperature. And because of the heat transfer in this direction, Q by convection, there is a temperature decrease up to here, up to here, up to here. So if you connect them, this is called boundary layer. Then there's something bothers you. What is that? Yeah, there's boundary layer. There's boundary layer. Are you happy? No. Then what do you want to do? This is called velocity boundary layer. And this is called thermal boundary layer. So there are two boundary layers for fluid flow over a surface. Then, one is about velocity, the other one is temperature, but we see they are similar each other, right? So is it possible to study this heat transfer from this boundary, the layer analysis that we studied from fluid mechanics? That was the idea. So how did we study fluid mechanics when we have a viscous flow over a surface? We used Reynolds number. Oh. Please talk to the president. We need a larger screen in this classroom. So in fluid mechanics, if you studied fluid mechanics, right? In fluid mechanics, we used Reynolds number to represent fluid flow over a surface. And we see they are similar to each other. The only difference is that is the velocity. This one is temperature. So maybe we can use the same dimensional analysis, but we just need to learn the difference between here and there. That difference, that ratio is called Prandtl number. So the ratio between velocity boundary layer and thermal boundary layer is called Prandtl number. So mechanical engineer a long time ago thought that maybe we can combine Reynolds number and Prandtl number to represent this heat transfer. That is Dusel number. Dusel number could be represented by Reynolds number times the difference between velocity boundary layer and thermal boundary layer Prandtl number, but not exactly Reynolds number times Prandtl number. Maybe one can affect more than the other. Okay, that's possible. So let's put M here and here, but still we need to match these two by the scaling down or up. So there should be another coefficient C. So that's how we developed this Dusel number correlation, C times Reynolds number to represent velocity boundary layer to the power n, and Prandtl number to represent the difference between these two to the power n. So that's how we developed Dusel number correlation. Then, once we know this is the basic form, then how can we determine C and N? You can perform an experiment. Prepare flat surface, provide a fan, blow air or water in this direction, and determine the heat transfer. That's how you can determine C and N. Can we do that? Can we do that? Yes. From where? Are you taking EGR456 thermal lab? There's a wind tunnel there, right? That wind tunnel can be used for fluid mechanics analysis, and there is a convection tunnel in front of that that can be used to study heat transfer. Then there should be a number of the scientists and engineers who are trying to determine these values. Some may be right, some may be wrong. So we are going to learn what is the most widely used Dusel number correlations. So that's what we are going to do in these chapters. But there are a few things that we need to know. So for example, how do we determine this Reynolds number? How do we determine this Prandtl number? So let's talk about Reynolds number first. This boundary layer develops in two different ways. The first one is laminar flow, the other one is turbulent. So the heat transfer characteristic of laminar flow and turbulent flow may not be the same, right? So we need to determine whether the fluid flow on top of this surface either is laminar or turbulent. So depending on laminar flow, there's a Nussel number correlation for laminar flow. There's a Nussel number correlation for turbulent flow. Which one are we going to use? It depends on whether our fluid flow is laminar or turbulent. So you should be able to, determine whether it is laminar or turbulent. And that is pretty simple. If it is external flow over a flat surface, Reynolds number can be determined by density times velocity times characteristic length over dynamic viscosity. That should be less than critical Reynolds number to be laminar flow. If it is greater than critical Reynolds number, it's going to be turbulent flow. In reality, it's not just laminar and turbulent, there's an intermediate. But that is too complicated, so we don't study that in undergraduate heat transfer. If you want to study that, go to graduate school. Then, is that important? Not necessarily. For most engineering applications, either laminar or turbulent are okay. So this is how we determine Reynolds number, and depending on the Reynolds number, you compare that Reynolds number with critical Reynolds number, you can determine whether it is laminar or turbulent. Then what is the critical Reynolds number? 4 more minutes, okay? That is 5 times 10 to the 5th, so 500,000. What is the unit of this Reynolds number? There is no unit for Reynolds number. That's a dimensional analysis. This Reynolds number, Nussel number, Prandtl number, they are all dimensionless. That's why you can use this one for this building. That's why you can use this one for myself, or Willis Tower in Chicago, or the different scales, because it's a dimensionless. Okay. So we learned whether it is laminar or turbulent, and depending on how heat is transferred, depending on boundary conditions, we have a different Nussel numbers. And the two main, the boundary conditions are uniform surface heat flux, uniform surface temperature. So depending on whether it is uniform surface heat flux boundary condition or uniform surface temperature boundary condition, you can, find different Nussel numbers. For example, if you, trying to cook something on a stove, you can control surface heat flux, low, medium, hot. That is uniform surface heat flux boundary condition. On the other hand, if you use maybe convection oven or something, you set a temperature. That's going to be uniform surface temperature boundary condition. So depending on how the heat transfer is going to take place, it can be either uniform surface heat flux or uniform surface temperature. So two things. We are going to determine whether it is laminar or turbulent. We are going to determine whether it is uniform surface heat flux, uniform surface temperature. There are Nussel number correlations. So how many? 1, 2, 3, 4. Already 4 Nussel number correlations. Okay. But before we, go to review, there's one more thing that we want to discuss. What is this mu? Dynamic viscosity. What is this rho? Density. These are material properties. Are they constant? No. They are temperature dependent. When temperature goes up or down, these values change. So you need to know at what temperature should we evaluate those material properties. In general, we use film temperature. What is the film temperature? The temperature inside the boundary layer. Then, what is the temperature of the boundary layer? Let's talk about that. Outside of the boundary layer is 90. Surface is 20. So what's going to be the temperature within the boundary layer? Could be 30, 40, 50, 60, 70, 80, and any number. But we don't want to randomly select them. So we assume that the temperature of the boundary layer is average between these two. So the film temperature is the average temperature between the surface Ts and T infinite. That's going to be the film temperature Tf. We use this temperature to determine material properties such as density, dynamic viscosity, specific heat, or thermal conductivity, Prandtl number, etc., etc. Okay? That's all you need to know before we introduce Lucent number correlations. Okay? So I'm going to stop here. We are going to continue this after Thanksgiving. By the way, any question about external force convection? It's going to be very quick. We just need to introduce these are the Lucent number correlations for these combinations. So use that. We are going to practice a few problems. Chapter 7 is over. And then when you go to chapter 8, these are the conditions and then these are the Lucent numbers for these conditions. Let's solve some problems. Chapter 8 is over. When you go to chapter 9, these are the conditions and these are the corresponding Lucent numbers. Let's use them to solve some problems. Then it's going to be over. So after Thanksgiving, maybe 1 class day or 2 class days, we can finish all 3. That's my plan. So basically, the final exam is not going to be that hard. You just need to learn, to know how to select the right Lucent numbers. But the problem is going to be the finding Lucent number is not the end of the story. Once you find the Lucent number, you determine H. Use that H. Find T or find Q. That could be the problems in the final exam. So final exam is kind of the extension of the second exam. Okay? Because asking just asking you to determine H value seems to be too simple, right? So that's my plan for the third exam. So now you know how important the second exam is, right? So I guess you have a pretty good idea about what's our plan for the third exam. And let's do a review for the second exam. I'm going to stop the recording. Actually, this review is going to be very quick. I'm going to introduce their